Hello, and welcome to another exciting episode of Arthur Does Math. I'm your host, Mr. Arthur, and I'll be the one you're forced to listen to for the next 30 minutes of your life. Enjoy. I'd like to start today with a question before we get into any of the guided notes. I want you to think about how you might approach a problem like this. 7 to the power of x equals this number that I didn't think about before I wrote it, 117,649. How would you solve for x there? Now, in some of our previous classes this year, we've looked at that, and we've pretty much employed a guess and check method, which you probably could pound your way through and figure out that x happens to equal 6. Okay, and that's nice, but that could be time consuming. That is always subject to your first guess and how close you are and stuff like that. But what if we push that one further and I said solve 10 to the x equals 2,000. Now feel free to try this one to your heart's content if you would like with the guess and check method, but it's going to cause you some problems. Okay? Guess and check is never going to get you there. Might get you close, sort of, but never actually get you there. So we need a new tool in our toolbox to be able to attack these functions and to solve for x. And that tool is called the log function. Okay? Now, you might know logs as these wonderful cylindrical looking things that often can be found in forests and riverbeds, and sometimes even be found lying on power lines when the weather turns bad. They seem to like to end up there. But we're not talking about those logs, as much as that would be fun. We're going to talk about the logarithm function. Now, you might notice on your notes that, there they are, that it looks like it's spelled logarithm. It is not logarithm. It is a logarithm. Okay? If you asked me, a logarithm would sound something like this. Isn't that catchy? That's actually a log drum played by a tribe in Africa somewhere. It's pretty cool. Okay? They definitely have rhythm with logs. But that's not what we're talking about. I'm really tempted to leave that as the background music for this whole video, but I fear that that might be a little too distracting, so we might come back to it at the end. Who knows? It might even become my theme song for this video. Anyway, logarithm is the inverse function of exponentials. And that's why we spent so much time talking about inverses, so that we could really get the idea that inverses undo each other. Just like adding 2 and then subtracting 2 undoes whatever you did, multiplication and division, squaring and square roots to a certain extent, not completely, cubing and cube roots, all those inverses that we've used before. Well, here's another one to throw in the box. You can kind of see some basic information about the exponential and the logarithm function, and we will get more into graphing at a later time, but the exponential function looks kind of like this, and you talked a little about that in secondary 1, and the logarithm is just its inverse. So it is going the other way, and for you visual learners out there, if you were to draw a line along the y equals x line, you could see that there's a reflection going there. So we're going to move on though to the definition of a log. We often shorten it as log. Feel free to call it log, so long as you don't think of the round cylindrical things. Now, logarithms have 3 parts to them in general. Okay. Whoa, crooked. Coming back. Okay. Logarithms need what's called a base. Okay. Now we often use a common base of 10. We call it the common log, or the natural log, which we use the base e. Yes, that's a number. That's another future topic. But logs can really have any base, and you'll see that today. Now, this is the definition of a log. Okay, this isn't a theorem. It's not an equation to be solved. This is what a logarithm is designed to be. Okay? You can switch them, so there's log form and there's the exponential form. Okay? And we're going to start using this. Now I know this is new to everybody. Okay? No one in my class at least has studied logs yet. So this tool is going to feel a little bit clumsy at first. It's like learning to use anything. You're going to fumble around with it at first, but you're going to find that once you are proficient with it, it's a really powerful tool for solving some things. So I'm actually going to write this at the top of every page so that you can keep looking back at it and reminding ourselves what the log is. So notice that the base of the log we write as a subscript, okay? And for log base 10, notice it's up here, we write that as just the log without any base to it. We actually have that function on your graphing calculators. This is my personal graphing calculator. It's my Ninja Turtle graphing calculator because it has a green shell on the back and because the Ninja Turtles are awesome. So you have this button right here, the log button. When you push that, it automatically does log base 10. You'll also notice you have the natural log button here, which, if you read further, is base E. Okay? All other logs you have to do a special workaround on the calculator or just do by hand. Okay? They are not pre-programmed in. But if you were wondering what those buttons did, we will come back to those later. Alright? So, next thing to notice is that we read this log base b of x equals c. I actually think that's worth writing down. So we would say this log base b of x equals c with a space there. Okay, or, you know, a lot of people shorten it log b of x equals c. We understand what you're talking about there. This one, we read this one the natural log, okay, the ln. Some people say ln, but it's really the natural log. Natural log as an L. Natural log of x equals c. Okay? So let's go on and practice using this thing here for a second. Here we go. Example 1. Rewrite each of the following in exponential form. So I strongly recommend that you write this at the top of your page. Log base b of x equals c. Now it said if and only if. We can also use a double-sided arrow. If and only if b to the c power equals x. Okay, and you'll be amazed at what we can solve when doing this. So the log base 4 of 64 equals 3. Now this is a true statement. It's an equation. We're not asking you to verify it or anything. We're just asking you to change its form. So if I follow my pattern, this is b, this is x, and this is c. So I can rewrite this as 4 to the third power equals 64. Feel free to verify that on a calculator if you will, but that is a true statement. 4 to the third power is 64, and we'd be done. Okay? Let's go to b. So b says log base 5 of 1/25 equals negative 2. Again, another true statement. So 5 to the negative 2 power equals 1/25. Okay, remember, a negative exponent causes us to be in a fraction, and 5 squared is 25. So we're good. Let's keep going here. Log base 65 of 1 equals 0. Well, that's always a true statement because, nope, can't say that. Most things to the 0 power equal 1. Not all of them. 0 to the 0 power does not equal 1. Don't let anyone fool you. It's a lie. It's not 1. Anyway. And the final one. This one just makes me happy. I mean, look at that. That's a smiley face on a math assignment. Like, you don't get those every day. You know this is special. So this is just so that you can see that it doesn't matter what we put anywhere. The equivalent form of log base triangle of smiley face equals star is, I don't want that, triangle to the star power equals happy face. Yay! Oh, it's too slow. Cue the music. Behold the power of logs. I wish you could see this guy jamming out on that video. He's way into it. It's awesome. Anyway, part of your assignment is going to be looking around and just changing the form so you get used to converting, because as we get into solving, sometimes it's more usefuler, however, it just sounded wrong for a minute. It is more useful to have it in exponential form than in log form, and vice versa for some other things. So let's go the other way now. Let's rewrite each of the following in logarithmic form. So again, this is our base. Okay, the base of the exponent is the same as the base of the log. Excuse me. This is our x right here, and this little 4 is the c. So we can write this as log base 3 as a subscript of 81 equals 4. Okay. Please make sure that's a subscript. There's nothing worse than seeing this equals 4, and then that is total garbage and a lie. So, bad things. Alright, let's keep going here. So I can do log, and since my base was 10, I don't have to write the 10. That is implied throughout all of mathematics, that if you do not write a base on the log, it is 10. So I'm just going to leave it alone. 1 over 100 equals -2. However, as you're getting more comfortable with these, if you feel the need to write base 10 to help you understand where it's going, it's not just magically disappearing, then I won't have any issue with that. Alright, so this one, my base is 6, so log base 6 of 6 equals 1. Again, because 6 to the first power equals 6. Anything to the first power is itself. And finally, m to the k power equals g can be rewritten as log base m of g equals k. Alright, any questions? Didn't think so? Good. Moving on. So there are some basic properties of logarithms that are always true, and they're, again, once you familiarize yourself with the changing of the forms, they become pretty obvious. So I want to try and make that clear though. So we assume where b is greater than 0, b is also not equal to 1, and x is greater than 0. A lot of that comes from the nature of the logarithm being the inverse of the exponential. I just want to flip back over here for a second. Just point out the graph. And look, if you notice, the domain of an exponential here is, well, it's negative infinity to infinity. But if you notice, the range goes from 0, not included, oh, here it is, up to infinity. Now, when we take the inverse, or find the inverse, we switch our x and y values, which causes us to switch the domain and the range. So the domain of the log function is from 0 to infinity, okay, and the range is negative infinity to positive infinity. So we can't have any of our input values of x being less than 0, okay? Coming back. And we want to keep all the values real. We like keeping it real, usually. So log base b of 1 equals 0 is always true. Anytime you take the log any base of 1, you get 0, because this is like saying b to the 0 power equals 1. Except again, b has to be strictly greater than 0. Alright, so we're not going to deal with that 0 to the 0 issue. So yeah, I think we all pretty much know that. Next one, log base b of b equals 1. Again, if you convert this to exponential form, you notice that you get b to the first power equals 1. So again, anything to the first power is no. Wow. Guys, call me on my mistakes. I keep telling you this. Okay, sorry. B to the first power is going to be b. It's just going to be itself. Alright? Property number 3, log base b of b to the c power equals c. Again, convert that. We get b to the c power equals b to the c power. Ta-da! And finally, this one is a property of logarithms, the logarithms in the exponent this time, but b to the log base b of x power equals x. Alright, so if you notice here, well, I know that those cancel out, but mind blank, timeout. Where did you go? I actually thought about this before, and that might be the problem, because I overthought it, but I didn't write it down. Okay. Cancel. I'm gonna feel really stupid right now. I'm the math teacher that just blanked on this property. But this is how you know this is live and this is real. Keeping it real. Anyway, I'm not going to spend too much time thinking about that. I know it'll come to me, hopefully by the end of this video. Okay? For whatever reason, I'm just not seeing it right now. Yeah, anyway, let's go on to example 3. That's embarrassing. Example 3 says, use the properties of logarithms to evaluate the expression without a calculator. So, all of these, it's like saying, alright, if you were to put this on here, we're trying to find what it equals, okay? Equals x, and we're solving for that x. We're only evaluating because the equal sign is implied and not already written there. So let's use the properties. Now notice there's nothing written in the base. This is base 10. So log base 10 of 10 puts us into the zone of this property right here. Actually, no, sorry, this one. We got the base and what we're taking it of as the same number. So this really does equal -4. This is garbage. What was I saying here? I need to go home. It's late. Alright, let's go to the next one. Log base 3 of 1. That's not the next one, that's C. B. E to the natural log of 6 power. So notice E is the base on the natural log. Okay, that's on the other page. But they do end up canceling each other out, and we are left with just 6 here. Okay. I mean, I guess the best reason that I can say right now, although I swear I had a more ingenious way of saying this, is that they're inverse operations of each other. If we are exponentiating with the function that undoes the exponential, it makes sense that they'd cancel out. It's like saying the cube root of x cubed. They're just going to undo each other, leaving you with that x, whatever you've got there. Alright, so now part C, we can say log base 3 of 1, looking up at our property number 2 here. Wow, struggle. Number 1. Any log of 1 is going to equal 0, so this thing is going to equal 0. D, log base 50 of 50. Here I have the base and what I'm taking the log of as the same value. So these are just going to be 1. Alright, log base 2 of 32. This one's sneaky. Alright, this is one where we easily could make it say equal x and then just use our property to flip it around and solve. But what they're really getting at here is that this is the log base 2, and if you think about writing 32, 32 is the same thing as 2 to the 5th power. So then we fall into the case of property 3, where I have the base and what I'm taking the log of as the same value, and so that just gives me 5. Okay, and then finally log base 4 of 1 over 64. Again, they're trying to hide it. They're hiding that we have a sneaky little 4 in here somewhere. It's like Halloween for logs. They're just all in costume today. We can write this as log base 4 of 4 to the negative 3 power. Okay, again, I know it was negative because I have a rational here, and I know 4 to the 3rd power is 64, so that's how I came up with that, and that equals negative 3. Alright, so I know you look at these and you think that it doesn't make any sense, or there's no way I would have seen that, and it just takes some practice, okay, and matching up different parts to the properties and talking about it with your friends and just practicing with this tool until it becomes second nature. Okay? I think it's time for a short break with more Logarithm music. Oh yeah, alright, I'm ready to go on now. Let's go to the back page. Come back here. Where are we going? Sweet. We've almost listened to a minute of log music. It's making my night. So, there is this principle of exponential equality, okay, that says that for any real number b where b is not equal to -1 or 0 or 1, we have this situation where b to some power equals b to another power, okay, then those two powers have to be the same. So long as the base is not -1, 0, or 1. Okay, and you can kind of see how that is. If I have -1 to an even power that's like a 2, and then -1 to a 4, they're both going to come out as +1, so that wouldn't work. 0 to any power other than 0 is just 0, so you could have different values for the exponents, and then 1 is kind of in the same boat where you could have 1 squared is equal to 1 cubed, and they're all equal to 1. But other than those values, this property holds. So I like how they put this here. In other words, the powers of the same base are equal if and only if their exponents are also equal. So what that means is that we can take this, and the first thing we want to do is we want to convert this back to exponential. If we're going to do things by hand, you're usually going to work with exponential forms at the end of the day. So I'm going to do 2 to the x power equals 8. So many of you can look at this and say, oh yeah, x is 3, which is true. Okay, x does equal 3, and by all means you can do that. But again, 8 is a sneaky little 2, just dressed up for National Log Day or whatever. So we can rewrite this as 2 to the x equals 2 to the 3rd power, which we already knew, so therefore that means that since the bases are the same, the exponents must also be the same, which gives us x equals 3. I know, that seems like a very roundabout way to get something that simple. You're probably right, but as we go on, you'll see how that can become useful. Sometimes things are even simpler than logs tend to overcomplicate a few things at times, so we can rewrite this one as 7 squared equals x, which you can look at that and handle. We know that x has got to equal 49. Alright, we keep moving through. Here we've got another x is in the place of the base, so I can say x to the 3rd power equals 125. Again, you might be able to recognize right away that x is 5. There's actually two ways to go about solving this one as well, if you didn't see that. The first is to find the sneaky little 5 in here and say that x cubed equals 5 to the 3rd power. Therefore, if the exponents are the same and they're equal, their bases must be the same. Notice this is an if and only if statement, and therefore that's like a two-way street, so you can imply both directions. You could also just decide to take the cube root of both sides. Equals the cube root of 125, and you still get x equals 5. So like I said, logarithms may not be the simplest way to look at things, but they are a very powerful tool when we need them. And today's just a basics day. I don't expect you to come away from today understanding why we need logarithms or when they're useful. I just need you to start using the tool. Start knowing the ins and outs of some of its properties. Okay, so here, when I get this situation, I hope that you're starting to get the hint that we're looking for sneaky numbers in disguise. 27, notice over here this was a base of 9, so I want to think, how can I maybe make these the same? That's a little tough. So maybe base 9 is not the way to go. Maybe they're both hiding something. So I want to think, is there a number common to both 27 and 9, maybe one of their factors, or something that we can look at? And it turns out there is. There's 3. Okay, so 27 is the same as 3 to the third, and 9 is the same as 3 squared. So I can take 3 squared raised to the x plus 1 power. And now I have a common base that I can work from, and so I can just look at the exponents. Please remember your exponent rules. When I have an exponent raised to another exponent, they multiply. So I get 3 cubed is equal to 3, and let's distribute that 2 to the 2x plus 1. Once we've established that, the bases are no longer really relevant to what we're doing, so I can come over here and solve that 3 equals 2x plus 1. Subtract my 1, so I get 2 equals 2x, and therefore, alright, what on earth did I do here? Anyway, are we seeing the problem here that I'm seeing? I hope you are. If x is 1, that means I plug it back up in here, and I get 9 to the 1 plus 1 is 2, so 9 squared is 81, definitely not 27. Alright. Oh, what a rough night. Okay, I didn't distribute. I put the line and I didn't make the distribution. Sweet. Okay. So, that means back up. Let's go from there. Alright, let's subtract 2. So I get 1, if I subtract my 2 here, equals 2x. And then dividing by 2, I get 1/2 equals x. Alright, that seems a little bit more reasonable. Alright, this would give me a 9 to the 1.5 power. Okay, always feel free to verify these on a calculator if you're a little concerned. If I go 9 to the 1.5, or 3/2, there's 27. Okay. Now I don't know that we would have guessed that, because we're really not used to dealing with exponents that are fractions or decimals. So that's kind of where the guess and check method starts to break down, and this property really becomes useful. And let's go to our last one. Alright, the log base 4 of 3x minus 2 equals 2 can be rewritten as 4 squared equals 3x minus 2. Alright, so fortunately we don't have to look for any sneaky numbers. My x is not in my exponent anymore, so we just solve this like a normal equation. 16 equals 3x minus 2. Add the 2. 18 equals 3x. How convenient. It's like someone planned it this way. We can divide by 3, and we can see that x equals 6. Sweet. Alright, so these are your basic properties of logs. Your assignment is going to be all about using the properties and really converting between forms. If there's anything that I could tattoo on your brain right now, as horribly painful and cruel as that sounds, it would be that log base b of x equals c means that b to the c power equals x. Alright, that's got to just be ingrained there. That's something you need to know and just be quickly able to transition between forms so that we can build off of that and solve a few more complex situations. So I hope that you got something out of that. I would like to leave you with about 20 more seconds of this really awesome log music. they have really cool hats too. Like I might have found my new heroes. I'm gonna take up log drumming, I think. Anyway, it's late, and I'm gonna go now.